Hi, everyone. Sorry, the folks part, I really don't understand. Okay, I just cannot adjust it. So this one is a little bit fuzzy. This part is very clear. Adjust the angle still does not work. And that's the best camera I can get, actually. I asked the technician again. They said that's the best they can get. It's automatic. I tried to get a manual one, but now they cannot find such one. Okay. Okay. So today we're discussing non-homogeneous recurrence relation. Of course, we consider linear one, all right, and these coefficients are constant. They are real numbers. Of course, this one is not equal to zero. The last one should not equal to zero. Otherwise, we can ignore this part. Okay. Now the difference is we have another term here, f of n here. So this can be any function of n, and it's not always zero. If it's always zero, then we have a homogeneous relation. So for non-homogeneous part, this part is not zero, not identically zero. All right. So we discuss things under this assumption. For example, here are three examples. So this is Fn. Here is n squared. Here is n minus 3 minus 1 to power n. Here is n minus 1. That's the 1 over n. All right. So here k equal here k equal 1, here k equal 4, here k equal 1. All right. Incidentally, this one actually is related to summation of this. That's the recurrence relation in connection with summation of this one, and last one is summation of this one. Harmonic series. All right. Now, for non-homogeneous ones, actually, it's very, very difficult. We don't have a general result for all possible f of n. But for some form of f of n, we have a general method. So that's what we are going to discuss. Basically, we only know when this one is of the form of polynomial function. So maybe denote by polynomial function of an exponential function. Let's see what I use this notation. So this part is exponential function, s is constant to power n, and here is a polynomial function. So here is let's see, p1. Maybe writing another way around. So this one denotes this function. So when Fn is of this form, then we have a general method to solve it. For example, for this one, we know how to solve it. For this one, we know how to solve it. But for this one, we don't know. This one don't have a closed form. We know that when n tends to infinity, this will be very close to log n. Actually, the difference is only all are constant. Roughly roughly this one, I forgot this is constant. It's all are constant. So it's roughly this one plus this one when n tends to infinity. So it's very close to log of n. We don't have a closed formula of this one. So name is we don't know how to solve this very simple recurrence relation. Of course, without this one, it's trivial. But with this one, it's very difficult. So that it depends on f of n. So in this case, we know how to solve it. We do have a formula for this one. We'll discuss it, how to obtain it. But for this one, we have no idea. The only thing we know is it's very close to log of n. All right. So in general, it's very difficult. So we only discuss a situation when Fn is of this form. All right. Now, before we can discuss this special case, let's get one theorem for this one. So any solution to this difference relation has a form that consists of two parts. One is this one is this one. Now this one is solution to the homogeneous part. This homogeneous part. So this one is a solution to this part. We know how to solve it. Then there are particular, so this homogeneous solution. That's why we use H here. And then there are particular solution for the whole thing. So in order to solve the whole thing, what we need to do is solve the homogeneous part without this one, which we know how to solve it. Then find a particular solution for the whole difference relation. Then any solution can be obtained this way. So that's a very general theorem, regardless of what f of n is. Okay. So I will quickly show you why this one is a case. All right. So suppose we to have a solution for this one, a whole thing. So suppose this one has a solution. All right. So this one we have a solution here. Now we have another solution. Suppose we have another solution. The Bn is another solution. All right. What we are going to show is this Bn can be represented as this one plus this one. So that shows any solution is of this form. Okay. So how do we do it? It's actually very simple. So by assumption this one is solution and this one is solution, we have two equations. So we replace an by this one. That's what we get. Plus f. Okay. So we know this one is a solution. So we replace an by this one, we have this equality. Similarly, we know this one is a solution. So when we replace an by this one, we'll get another equality. We have bn equals c1 bn minus 1 plus ck bn minus k f of n. Because both are solutions, both satisfy this relation. All right. Now we subtract this one from this one. So what we get is so these two fn cancels. So that's what we get. All right. So what does that mean? That means this one is a solution from homogeneous part. This is a solution of this one. So this is a solution of homogeneous part. So that means because this one is a solution from homogeneous part, which is this one. So therefore, by changing, we get Bn equal let's see minus hold on. This one. Y isn't plus to the solution. Okay, hold on. Let's see. I think I may miss that. Let's see. So one is this one will not give us what we need. This no, let's see. Let's see what's Okay, so something. So this one is solution for the homogeneous part. This equal homogeneous part. Mm, yeah, and it's another solution. There's something right. I did not see it. Let me see. Okay, A and P minus A and H. That's not what I want. Should be plus. That's what I want. Let me check. Okay, something here, and everything has this form. Particular solution. By this one, Pn is another solution. Also by this one, went to minus. This one is solution of homogeneous. Yes. Let me check. Okay, I think something is here, but something is. Oh, okay. Yeah, okay. Okay. Actually, it's correct. This is a symbol. Okay. Minus plus. It's of this form is just minus plus. Okay, let's just do another way around here. Instead of this one minus this one, what I do is this one minus this one. Just fine. Okay, it's minus plus same thing. So here, instead of doing this equation minus this equation, what I do is reverse it. Okay, so here will be it's just minus sign. Otherwise, they're not good. B and minus A and P. Okay, good sign. So here will be do it this way, then I get minus instead of probably get plus instead of minus. Okay, here the E n minus K minus A E n minus K. All right. So then I get here. Okay. So then here it becomes plus. It's just sign difference, but not matter. Actually, same thing, just sign difference. Okay. So it's a plus minus the same thing. Just this one I change it. So if originally if A and H sorry A and H is solution now minus of this one is solution basically what it means. Okay. So now it becomes this form. So any solution will be of this form. This one plus this term. All right. So to better maybe revise this one as it's same thing. Okay. Particular solution plus this one. But here like a homogeneous solution plus particular solution. But that's very general theorem. Regardless of the function f of n, we always can say that any solution will be of this form. Solution to the homogeneous part plus a particular solution. The summation of these two terms. Now, by this summation, actually, originally it's also like flat when they said minus. This plus, but when I write this form, this one, if I write here minus here, so this may be negative. So just change the form. It's still of this form. Okay, does not really matter. But this one looks better. You use plus sign here. All right. Okay. So we know every solution will be of this form. So therefore, in order to solve this differential relation, what we need to do is find a particular solution for the whole thing. Then we know every solution is of this form. Since we know how to solve this homogeneous ones, so the remaining thing else is how to find a particular solution for this. In general, we have no idea actually. But for special forms of this, when it's in this form, then we know how the solution looks like. Right? That's it to write maybe H first, and T. All right. So now we assume this one is of this form. So S is a constant, S is a real number. B is a polynomial of degree T. Okay, B, T, polynomial. All right. In this case, the particular solution basically is of this form. The solution of the whole thing, particular solution basically is of this form. So what we have is two situations. One is when this S is the root of the characteristic equation. I'll multiply the m, then we'll need to multiply it by this n to power of n. So in this case, S root of characteristic function equation. All right, otherwise we have this, as it's not root, we have this situation. Maybe otherwise I spell it. Write it down, okay. All right, so I only have two situations. Now, the form of the particular solution is exactly the same as the form of this one. It's a polynomial of degree t times s over n. S for s to the power of n. Here, p of t denotes a polynomial of degree of, sorry, this one is polynomial of degree t. Okay, so this one is polynomial. It's polynomial of n to degree t. Okay, so the main part is same, exactly same as this one. But the coefficients of the polynomial needed to be determined. Coefficients inside here may be different from here. So that's why here we use b, we use p here. So they may be different. But the form is exactly the same. Now, depending on whether s is root of characteristic equation, if it's a root, then this one will be have n to power m here. If it's not root, then we don't have this term. So that's the only difference. Only two cases. Okay, one is when this s is the root of characteristic equation, then we need to multiply it by n to power m. Otherwise, we don't need this term. So basically, that's it. Now I give you a few examples to make things clear. Give you a few examples, maybe two or three examples. Let's see. There's only two cases. All right, let's consider the following. So here Fn, let's say, plus Fn, okay, something. Like you will we will define the particular solution for this one depends on different forms of this one. The homogeneous part is this one. This homogeneous part. All right. Now characteristic equation is r squared minus 6r plus 9. This is the characteristic equation. So that gives us root r3 I equals 3. We multiply the 2. So we have two identical roots, 3. All right. So that's the situation. Now for different value of f of n, particular solution will be different. Now for homogeneous part, solution for homogeneous part, we've learned Monday already. Solution of homogeneous part will have the form n, 3 to power n. Here is multiplicity 1. So then there are the polynomial of degree 1. So we have alpha n with the space alpha n plus 3. So that's a form of homogeneous part. These two numbers, alpha beta, needed to be determined based on initial conditions. But it will be of this form. All right. So which we know already. Now for the particular solution of this one. So we're looking particular solution of this one. So that depends on form of f of n. So let's consider a few possibilities how the solution look like. Maybe start with 3n. Maybe don't start with 3n. Okay, don't start with this. Okay, maybe start with let's see, root 3. Okay, start with this one. So Fn is on this form. Now this is S. Okay, so this one is S. S equal 2. So in this case, S equal 2. Which is different from root R. So therefore, particular solution will be of this form. Here is a quadratic polynomial is second degree. So we have a second degree of polynomial times this one. Solution will be the form polynomial here second degree P0 plus P1n plus P2n squared. So that's how its solution look like. All right. Now these three numbers need to be determined. I will show you how to determine these three numbers. All right. But this is a form of particular solution. Now consider another one, 3n. So in this case, s equals 3, which is same as the root. Which is same as the root. Root is 3, or multiplied is 2. So here is 3. All right. Now this form needed to be multiplied by n squared. Just multiplicity here too. So it will be of this form. All right. Now here is a polynomial of degree 0. So that means there are constant here, degree of 0. So in the original, in the other system, the way we use it, maybe to better write this one, P0. So this P0, the number needs to be determined. Okay, for one more example, n 3 to power n. So again, s equals 3. So again, we'll have this one, n squared over here. Now here polynomial is degree 1. So here we have a polynomial of degree 1. P0 plus P1n. That's how it looks like. All right. Now finally, let's take a look at this one, 3n. Okay. So this one, generally when we discuss it, we say Fn in the form of polynomial times Sn. Now in this case, this one does not seem to have this part. What does that mean? Actually, that means this one S equal 1. So it's very important. In this case, what does it mean? Is S equal 1. Okay. And next example, you will see the subtlety. S equal 1. Actually, that determines whether some time needed to multiply by n not n to power m or not. Okay. So in this particular case, 3n means 3n times 1 to power n. So then in this case, S equal 1. 1 but not equal 3. The solution will be of the form of this one, the same as this one. So that is polynomial of degree 1. So it will be of the form of this one. Okay. So of course you want this one, and you can write this one, but of course this one still is 1, so we don't need this part. So it's really a polynomial here. All right. So basically, the form of particular solution is determined by form of Fn, and whether S is a root for characteristic equation or not. So we have two different ones. All right, I think we have time to give you two actual examples to see how it works. In the tutorial tomorrow, I will ask a tutor to give you some working examples. The tutor will go over several working examples. All right. So today, I don't think we have too much time to go over all the details, but I think I will. Yeah, we should have time to go over this. So for example, I mean. This part actually is quite easy because there are formulas, you can just follow it. The only thing is you need to be careful. Other than that, it's very simple. It's mechanical and simple, but you need to be careful. Okay. So let me give you an example. Okay. Yeah. Perhaps I should follow example from textbook instead of a brand new one. I'm not sure whether I will not make any mistake in the middle at all. But these calculations, I'm not good at it anymore. I'm not like 20 years old. Okay, I'm almost 60. Anyway, I just use the example from textbook. All right. So in order to avoid the mistake, I just use A1 equals 3. Let's see, it's the one. AN 3N. Okay. So for this non-homogeneous difference relation, we try to get from the formula. So for this one, the characteristic equation is very simple. So it's homogeneous part is just this one. So here is characteristic equation. So we have root equals 3. All right. So homogeneous part will have the form here 3 to power n and the constant. So we have this form. So that form from homogeneous part. Right. Now for the non-homogeneous part, so it will be of this form. Should I try the other one? This one is kind of too simple, maybe. Okay, instead of this one, okay, let's stay on this one first. So this one will be polynomial degree 1. So it's we use alpha already, so maybe use Cn C. Here, remember it's 1 to power n. So this one is same as 1 to. So f equal 1 to. So 1 is an upper loop. So it will be of this form. All right. Now we have the form for both the homogeneous part and non-homogeneous. Now, how do we find these values? So we know their form, but we need to determine these values. How do we find these form values? We'll need reference relation. So typically, one way to do it is starting from this one first, determine these values first. So how do we determine it? Because this one satisfies this equation. So we replace an by this one, then we'll try to obtain C and D. Okay. So let's see. So in the places AN equals CN plus D, which equals 3 AN minus 1 CN minus 1 plus D plus 2. Because this one is a solution for this one. So certainly satisfy this equation. So we can replace AN by this one. That's what we get. All right. Now this one, let's see. So it's 3CN minus 3. All right. Now just some manipulation. Then we reorganize this one and organize it into the following form. Let's see. So with N, so we put everything with N together. That's the Cn minus 3 Cn here minus 2n. So that's everything with N. All right. So everything without N here is D plus 3C minus 3. Okay, so here's everything with N, here's everything without N. So here, everything with N, we have N, we take it out, minus 2C minus 2. So here, plus 3C minus 2. Here. All right. Now, for this one to be identically always to be 0, what we need is this one, both of them equal 0. So then we get a system equations. So we get two equations. Minus 2C minus 2 equals 0. 3C minus 2D equals 0. All right. Now we solve this system of linear equations. What we get is C equals minus 1, D equals 3, 2. Is it minus? Yeah, so that's what we get. All right. Now, in order to determine these two coefficients, what we do is in this polynomial, we write it as a polynomial. So here is degree 1, here is constant part. Now the coefficients of each part needed to be 0. So we get a system of linear equation. By solving the system of linear equation, we get these numbers. All right. So after that, we know that indeed so from here we can so that's our particular solution. Okay. Now we know the solution. Our solution will be of this form: 3n minus n 3, 2. So that's our solution. Our solution should look like this one. Homogeneous part plus non-homogeneous part. Only thing remaining is this constant. Now we use initial condition to determine this constant. So A1 when n equal 1, we have A1, which is 3 alpha here 3 minus 1. That will allow us to determine alpha equals something. Let's see. Oh, yes, a fractional number. So eventually, we will be able to get our solution, which will be an equals minus n. So eventually, we'll be able to obtain this one as solution. Okay. So see, the idea is not difficult, but here involves two equations in order to obtain the coefficients. One is a system of linear equation. One may be a system of linear equation here to determine constant on homogeneous part. So here for non-homogeneous part, here is for homogeneous part. So one there needs to be careful, otherwise easy to make mistakes. All right, okay. So really you have to do a lot of practice in order to know how to do it. Otherwise, oh, I remember the idea. Otherwise, you easy to make mistakes, and perhaps you don't know how to find these things. So really, the homework assignment is very important. All right. So I'll give you one more example to finish today's lecture. We want to obtain a closed formula for the square of both n numbers. All right. So one way to do it is use the recurrence relation. Okay. So we have a very simple recurrence relation. Here, Fn is non-homogeneous one is n squared. Now, if you recall the basic method to solve it, we can use iteration method. You can try to use iteration method to solve it. But eventually, what we need is to compute the sum of this one. So that method does not help us. Luckily, here we know how to solve this one using the formula for non-homogeneous ones. Okay. So first, for homogeneous one, the characteristic equation is r minus 1 equal 1. The root is 1. The homogeneous part. All right. So homogeneous part will have a form. No need to use. Homogeneous part is just a constant times solution raised power to 1 to n, so which is same as b. This homogeneous part. All right. So we know the form of homogeneous part. Now for non-homogeneous part. For non-homogeneous part, this one. Now here it's very important. This one is same as n squared times 1 to power n. So remember, in our formula, Fn has a form b of t times s to power n. So that's s. Here s equal 1. In this case, s equal r. So that means homogeneous, a non-homogeneous part for particular solution of this one will be of the form of this one times n. So it's n times f of n. So we have this form. The form looks like this. I mean the form, okay, not exactly this one. So this one, form of this one is the quadratic function, here n squared. So here will be quadratic function a n squared plus en plus c. The particular solution will be of this form. All right, of course, it's equal to a n cubic plus b n squared plus c n. All right, so now we know the solution will look like this one and this one plus this one. So we have 4 constants to determine. If we follow the previous example, in order to determine this one, we can plug in here. All right, so in order to determine this one, so this one must satisfy this equation. So we have this one From here to a complicated manipulation, we'll be able to become A and B and C. You see, it's not easy. It's tedious, it's complicated, right? Because we have to come to all these things. For this particular example, a best way is the following. So here, for the homogeneous part, all right. So actually, we can find that B equals 0. Because of initial conditions of S1 equals 1, if we look at S0, it's equals 0. All right. So if it has this form, plus B, okay, so let's erase it. Sn. If Sn equals this one, when n equals 0, the value is 0, so that means B equals 0. So here we can obtain B equals 0. So this one actually equals 0. So S0 equals 0 will give us B equals 0. All right. So actually now the situation looks like this. We obtain value for one constant already. So we have 3 values. So how do we determine these 3 values? Use initial condition. So in order to find this one, we determine use S1, S2, and S3. Use 3 equations. So S1 equal 1, S2 equal 1, 2 squared 5, 9, 15. 1 square plus 4 square 5, 9 is 14. 15, right? Sorry, 1 plus 4 plus, it's 14, sorry, it's 14. Now here, instead of going through this one, we use these 3 initial values to obtain system of linear equations. So for n equal 1, 2, 3, that's what we get. So let's see, 1. Here 2. So we have 3 linear equations. Okay. So you see, it's quite, again, it's so instead of do algebraic manipulation here, what we need to do is to solve the system of linear equations. Use Gauss elimination or whatever method you use. It can be done, okay? So this one can be done. Let's see how I did it. I eliminate the C first, okay? So what I do is eliminate the C first. I get 6A plus 2B equals 3. 18A plus 4B equals 8. So I eliminate C. That's what I get. Then from there, one can get A equal 1/3, B equal 2/3, and eventually C equal 1/6. All right. So then one can obtain our solution and follows. So this one. So maybe the familiar form actually typically you see one is written this way, n plus 1 to n plus 1. Just perhaps the form you have seen. So now we will be able to get summation of first n numbers, the square of the first n numbers. But here the formula on this. So using your first relation. All right. Okay. I think I will stop here. Let me emphasize again, this part is tedious and tedious mechanical. It's not that interesting actually, but it's very important. You at least you have to remember forms. All right. So typically we'll deal with, if I can, I think typically at most homogeneous part may be quadratic equation. Other than that, it's too difficult. So in homework, maybe I will give you, I don't think I give you more than two. If it's more than two, then I will give you roots because it's not easy to find roots for the polynomial degree more than two. So typically you should be familiar with the polynomial of degree two. So the cancellation only, the dependence is only on the previous two terms. Okay. And tomorrow in the tutorial, tutor will give you a few more examples. Actually how to compute solution, determine the coefficient, maybe 3 or 4 examples, I think, within an hour, at most 4 examples, I guess. Okay. So if you feel comfortable, familiar with this one, then you don't need to attend the tutorial. But if you want to see the details of how to obtain these things, then you should attend. Okay. So the basic thing behind it is solving system of linear equations and solving polynomial equations and the roots. Then use the formula. Okay. All right. Okay. So that's it for today. See you next week. Okay.